Alright, so for this video, we'll be looking at standing waves. They're also called stationary waves, so your teacher might have called them that, but I will be referring to them as standing waves throughout this next few videos. Alright, so for this first video, the way I'm going to introduce it is I'm going to compare the differences between our regular waves that we've looked at so far, so those are our progressive waves, the ones that move, and compare them to our standing waves, so the waves that don't move, or don't appear to be moving. Alright, so firstly, I'm going to make two categories, so we have our progressive waves, and then our standing waves. There we go. So here you can see an example of a progressive wave where it has no end, so the wave just kind of goes off into infinity. And you can see there, this is a transverse wave, and like I said in the previous video, you can see how the matter is not changing, however the energy of the wave is traveling. Now let's try to set up a standing wave, and as you can see, it's kind of formed a standing wave. You can see here how instead of the wave progressing, the wave kind of looks to be staying in place. You can see how the point of max displacement over here and over here, so those are our antinodes, and our point of zero displacement at the ends and in the middle also stay stationary, right? And so you can see what I mean by a wave that appears to be standing in place rather than traveling across. So based on that, we can see that progressive waves transfer energy. So like I said in that display when I showed the progressive wave, you could see that the matter itself did not change, that the beads themselves stayed in the same spot. They just moved up and down. They just oscillated up and down. However, the energy of the wave was traveling into the abyss, okay? However, standing waves, on the other hand, have contained energy, right? So what that means is that the energy just stays in the system. And you could also see that in the demonstration. So with the progressive wave, we can also say that the max displacement traveled across the wave. And so the amplitude is the same at different points of the wave. Okay? However, in the standing wave, again, we saw that there were places where there were max displacement, and there were also places where they had no displacement. And so the amplitude is different on the wave at different places. Again, when we compare that to the standing wave, even though there's only max displacement at, let's say, 2 points, let's say we have a wave, okay, and this is a progressive wave, so it's moving this way. Even though there's only max displacement at 2 points, we know if we give it some time that the max displacement will shift to this point, right? From here to here, and then from here to here. As we saw in the standing wave, the max displacement, if we give it some time, it will remain in these positions, okay? And the places of zero displacement will also remain, okay? So again, amplitude, different at different places on wave, okay? And so in other words, standing waves have fixed points of nodes and antinodes. Of nodes and antinodes. And just a reminder, a node is a place of zero displacement, and an antinode is a place of max displacement. All right, and then obviously, by contradiction, traveling waves do not have fixed points of antinodes and nodes. Okay, and the main and key idea of standing waves is that standing waves must have interference. Okay, so I'll go into what interference is later on. And in order to have interference, we must have two sources. Okay? Alright, so what is interference? Okay? Interference or superposition, either one is fine. So interference or superposition is when two waves meet at a point. Okay? And so what I mean a point is just a location. Okay? And when these two waves meet, they interfere. And when I mean they interfere, I mean that they superimpose onto each other. Okay, now superimposing is if I have something and then I put that thing on top, right, like that, that's superimposing, okay? And so what this results in is that the resultant, okay, resultant just means the final end product, the final result, okay? The resultant displacement is the sum of the individual displacements, okay? All right, so what that means is that, let's say, we have a wave, okay? And this wave is moving this way. And we have another wave, okay? Like this. And we can say that these two waves have the exact same wavelength and the exact same amplitude, okay? So they have the same wavelength and same amplitude, okay? And this wave is moving this direction. So let's say we give it some time, some arbitrary time. We will eventually have a case where these two waves meet like this, essentially, right? That's the best drawing I could do. But those two waves are meeting at the exact same point, right? Like I said here, when two waves meet at a point, that is this situation right here. We are meeting at a point. So let's look at the definition. When two waves meet at a point, they interfere and they superimpose, okay? And the resultant displacement is the sum of the individual displacements. So because one is quote-unquote going up and the other one is quote-unquote going down, so this top one is a crest and this one is a trough, their individual displacements are in opposite directions, right? And if we add two equal values, so like I said, their amplitude and wavelength are the same, so two equal values in opposite directions, their values will cancel out. And so the resultant displacement is 0. There'll be no wave. They'll cancel each other out. All right, and this is what's called destructive interference. All right, destructive interference. Now, it's also important to note that this only occurs when the two waves meet at a point. Because this wave is moving to the left and this wave is moving to the right, after they meet at this time, the two waves will continue on their way, and this wave will go like this, continue, and this wave will continue on its way, okay? So we can call this T1, T2, and T3. So at T1, they're coming towards each other, and at T2, they meet at the exact same position, at the exact same point, and so they superimpose and result in destructive interference, and so there's no wave, the waves cancel out. And then at T3, they both continue in opposite directions, right? In the same directions that they were moving previously. So that's our first scenario. Our second scenario, we can have the exact same wave coming up like this, moving to the right again. But let's say we have another wave on a string again, also moving in opposite direction. However, this time, they are both crests, right? Both are crests. And again, these two waves have the exact same amplitude and the exact same wavelength. All the same properties, okay? In this case, again, this is T1. And if we move to T2, where they meet at the exact same point, right? So this is wave 1, and we can label this as orange, okay? So this is the second wave. They meet at the exact same point, and because of that, they will superimpose and interfere, and therefore resulting in a bigger wave. Now, because these two waves have the exact same property and the exact same amplitude, the amplitude of this wave would be 2A, okay? Let's say this is A, and then this is also A. Because they superimpose, the resultant will be 2A, because it's the sum of the individual displacements, okay? Now, it's not always 2A, so don't take that as something that will always be true. This is just for this example because they have the exact same amplitude, okay? And once again, at T3, once they are no longer meeting at the exact same point, this wave will continue on this way, and this wave will continue on this way. And this is called constructive interference. And that will be it for this part 1.